Welcome to one more session of Introduction to Photonics. So, what we want to do during this week is identify the fundamental principles of lasers and quantify their performance characteristics. So, that's what we want to get to, and we do understand that a laser is essentially an amplifier with feedback. So, we have been spending a lot of time trying to understand amplifiers, understand the process of amplification, and we have some unfinished business from that perspective. So, in the last lecture we were trying to address a problem related to the design of an erbium doped fiber amplifier. So, we said erbium doped fiber amplifier construction is typically like this, where you excite the erbium doped fiber from one of the ends of the fiber, because this lateral excitation is not practical. And when we do that, we started looking at how the pump power is getting absorbed along the length of the fiber, and also how the signal power evolves along the length of the fiber, and we needed to quantify how the signal power evolves. So, in order to do that, we were defining the signal power along the length as dps over dz, which was essentially dependent on this gain coefficient. Now, this gain coefficient itself, one thing that we realized is it is N2 multiplied by sigma E, as it is mentioned over here. It is N2 multiplied by sigma E minus N1 multiplied by sigma A. Previously, we had made a rough approximation saying sigma E is equal to sigma A, right. But if you actually write it out, the gain coefficient would depend on this factor in the square brackets, and what that tells us is that it is not necessary that N2 is greater than N1. So, we looked at specific conditions where if sigma E is greater than sigma A, okay, then N2 need not be greater than N1, and conversely we said if sigma E is less than sigma A, if you have sufficiently high N2 over N1, you can achieve gain, right. So, we ended at the point where we were pointing out to certain spectral regions where in the longer parts of the spectrum, the longer wavelengths, we find that sigma E is typically greater than sigma A, and because of that, for very low levels of excitation you have gain, right. Whereas the shorter wavelengths over here, we have the case where sigma A is greater than sigma E, and it takes a high level of excitation. So, we were plotting this as for different levels of excitation, and we said it requires a fairly high level of excitation to get gain. Gain is defined by this line. So, above that you have positive gain, which means amplification, and below that we have negative gain, which essentially means loss, right. So, it just tells you that you have to look at the relative levels of sigma E and sigma A to, and as well as the relative levels of N2 and N1 to determine what N2 versus N1 you need to achieve gain. The question is about the absorption coefficient, which is essentially the number density multiplied by the transition cross section, right. So, N1 sigma can be looked upon as the absorption coefficient, yes. So this is you can just say it is basically the emission coefficient versus the absorption coefficient, right. But just to visualize all of this or help the visualization, I have actually drawn all the energy levels. So, it is such that the ground state is to the right side of this graph, and as we go towards the left side you are increasing in energy, right. So, if you are going from if you are pumping with 980 nanometer photons, you are going to that higher energy level which corresponds to the leftmost features, right. And then from there you are non-radiatively relaxing to this other energy level which we call as energy level 2, which is not just a single energy level. I wanted to emphasize that it is actually a bunch of energy levels there. So, you could have transitions over a wide range of wavelengths. Okay. So, essentially you can get gain over a wide range of wavelengths. Okay. So, and one important thing is what is happening at this point, right. So, it says that irrespective of your pumping level or irrespective of the fraction of ions at the excited state, you cannot achieve gain at 980 nanometers. Why is that? Well, there are two aspects to it. One is that we have a very strong non-radiative relaxation component, right. So, you are not actually achieving emission at 980 nanometers, right. And but even if you end up getting emission, it is essentially corresponding to a 2-level system. So, there is equal probability of having the erbium ions at the excited state and as well as the ground state. So, unless you have a significant emission cross section, right, you cannot achieve gain. And in this case the emission cross section, that is the first statement we made, is very low because of the fact that the non-radiative process is actually a much more likely process than emission back to the ground level. You understand this? Okay. So, let us actually go back and see if based on all this discussion whether we are able to solve this problem. This is where we started in the last lecture. So, we are asked to consider the amplification of light at signal wavelength of 1550 nanometers. You are given the total doping concentration Na. You are asked to assume uniform excitation. Okay. So, that is actually a key point over here. So, if you have uniform excitation, what can you say? That the inversion is actually uniform across this entire length of the fiber, or you can make an assumption like that. And because of that, if we go back and look at this, we can say that with under uniform excitation, you can say that N1 of Z is just constant, N2 of Z is a constant. So, there is no length dependence on the inversion, and because of that integral will just yield a value of L. right. So, that is what is uniform excitation would correspond to. And you are also told that you can assume a pump signal overlap factor of 0.9 for the erbium silica fiber. So, what does that correspond to? So, I have drawn the cross section of the erbium silica fiber. Okay. So, we are looking from the side of the fiber, and so we know that you have a core and a cladding, and the core essentially consists of all these erbium ions, which is actually, like I said in the last lecture, is triply ionized, so erbium 3 plus ions. But what can we say about our light distribution, especially the fundamental mode? When you talk about the signal fundamental mode, that mode is not completely confined in the core, right. So, there is certain parts of it that is in the core, or most of it is in the core, but there is a certain fraction of that signal which is propagating in the cladding. So, what can we say about that as far as an amplification process is concerned? That part is not actually undergoing gain, only the part that is going through the core is undergoing gain, right. And the other aspect is that you have a pump and a signal, and your gain would depend on what is the overlap of the pump and the signal. Why? Because if your pump is like this, right, which has got a peak corresponding to the center of the core region, and over the periphery the amount of pump intensity available is lower, then the inversion is lower in those areas. The inversion is very high in the central area, the inversion is very low at the other side. So, your gain once again actually depends on what is the pump profile, or specifically what is the overlap of the pump with the signal, right. So, we are taking care of all of this through this pump signal overlap factor, which we will denote as capital gamma, and this overlap factor is such that when we are defining gain, if we go back and look at this, when we are defining gain over here, or when we are defining the power itself, you have to multiply that gain coefficient by that pump signal overlap factor, right. That overlap factor is a number between 0 and 1, typically on the higher side, because your signal, if you have designed your fiber correct, your signal will have a fairly good overlap with your fiber, and the pump will also you design the fiber such that the pump has a significant overlap with the signal as well. Okay. So, you have to multiply that gain coefficient by that factor. So, if you go back and look at all of these things should have that factor capital gamma in that, which corresponds to the pump signal overlap. So, the question is whether gamma will be constant throughout the fiber. Yes, you can assume that, right, because for a given fiber, the mode profile does not change as along the length of the fiber. So, the gamma can be assumed as a constant along the length of the fiber. So, the question is, the fiber is designed to be single mode for a particular wavelength, and in some ways does that hold good for the pump also, right. So, that is certainly a good question, because we do know that the mode profile depends on the mode field diameter depends on the wavelength, right. So, you have for longer wavelengths you have larger mode field diameter. Okay. So, typically you do design such that it is single moded for both the pump as well as the signal, right. And if you are single moded for the pump, that means the signal at the signal wavelength, you are still single moded, because anything longer than that you are still single moded, but more energy will be in the cladding region, will be propagating in the cladding region. But at the end of the day, you do have to, when you are designing an amplifier like this, you are making these splices at the ends of the fiber, and the splices are with regular telecommunication grade single mode fiber, right, and that fiber has a certain mode field diameter. So, you need to maintain that mode field diameter in this fiber itself also, right. This erbium silica fiber also has to be mode matched with that telecom fiber, and that is a challenge, because if you are mode matched, then essentially either your pump, because your regular telecommunication grade fiber has a cutoff wavelength around 1200 nanometers. Okay. Now, if you use the same or a similar type of fiber, you will end up having slightly multimode for the 980 nanometers. You have one higher order mode also possible, and that might affect the pump signal overlap factor. Okay. So, those are all certain design considerations that you have when you make this erbium silica fibers, but yeah, that I just wanted to make you aware of this. We are not designing the fiber itself at this point. Does that answer your question? So, how do we include this pump signal overlap factor? We said, okay, we are actually multiplying this by gamma, and so that is what is given as 0.9 in our question. But the when we look at part A, it says basically write down the expression for the small signal gain of the amplifier in terms of fraction of ions in the excited state with respect to the total doping density. So, what we are asked to do is to write this expression in terms of the fraction of ions. So, the fraction of ions in excited state is N2. So, N2 is such that N2 equals to N2 over Na, right, wherein Na is the total number of ions in the fiber. So, or in other words, N2 can be written as N2 multiplied by Na, and N1, what can we say about N1? So, that is going to be 1 minus N2, right. Whatever is not in the excited state has to be in the ground state, right. So, 1 minus N2 multiplied by Na. I should say it is approximately, because this is under approximation, that N3 equals to 0, right. So, instead of N1 and N2, I can substitute this expression, and so what you get for what we considered here is G is going to be given by gamma into N2, well, instead of N2 I can write as 1 minus N2 Na sigma ES minus no, this is sorry. This is N2 Na sigma Es minus 1 minus N2 Na sigma As multiplied by L, right, and the entire thing is under an exponential. Okay. So, I can simplify this, and I can just write this as G equals exponential of gamma L, capital gamma L Na sigma Es plus sigma As multiplied by N2 minus sigma As. Right, I just rearrange terms. So that is a little more convenient to use, right. Basically the gain, it just now you have a certain gamma for a given fiber, the gamma is given, what is the length of your fiber, what is your Na, the total number density of ions in the fiber, erbium ions in the fiber, and then you have your cross sections. So, in this one the only variable is N2, right. So, you can now calculate G for different values of N2, and especially if you want to do this in dB scale, the gain in dB scale, it has got to be, so it is basically 10 log 10 of exponential of all of this. So, what is that going to give you? Is basically it is going to give you 10 log 10 E, right, multiplied by this factor that is in the flowery parenthesis. So, 10 log base 10 E is what? What is the value of that? Huh? It's a tabulated value, right? 4.343, right. So, multiplied by this entire factor over here. So, this is going to be given by multiplied by gamma L Na sigma Es plus sigma As N2 minus sigma As. Right. So, and if you of course want to take out the length dependence, you can express this gain per meter, right, and then the rest of that stuff will remain as it is, right. And this is what we have represented over here. In this plot, what we have represented is gain in dB per meter as a function of wavelength and as a function of this excitation level, which is N2. So, excitation level N2 equal to 0, which corresponds to 0 ohm power launched into the fiber, to excitation of 100% where N2 is equal to 1, right. So, those are the different cases that are being represented over here. You understand this? So, for the given problem, we can actually use this graph to find out certain values. Okay. So, what are the values that are being asked? First of all, we are asked to come up with this expression So, that is we have done that, we have looked at the gain expression as a function of N2, okay. And then when we go back, the second part is the plot below, actually the plot that I showed just now shows the gain spectrum for different values of fraction of ions in the excited state, right. Lowest curve corresponding to 0% and topmost corresponding to 100%. Determine the absorption cross section and emission cross section at the signal wavelength. So, emission and absorption cross section are not given, you are just given this graph by the manufacturer, okay. Now, can you estimate the emission and absorption cross section at a particular wavelength? We have been asked to consider 1550 nanometer as the signal wavelength, okay. Can we get that? How do we get that? You need to essentially estimate these values. Given a graph of G versus or G over L, because gain in dB per meter, that is given as a function of N2. Yeah, any ideas? So, first of all, let us substitute N2 equal to 0, okay. If N2 equal to 0, then whatever the gain value, it represents only this factor, right. So, and everything else is known, gamma is given as 0.9, L we do not have to worry about because G over L is what we are computing, okay, and Na is given, right, and then the only unknown is sigma As, so you can find out sigma As from that. So, that just corresponds to at 1550 this point. So, at that point the gain is minus 3 dB per meter, okay. So, I will just go back to this expression and say for N2 equal to 0%, the gain is given from the graph, you can read from the graph, is minus 3 dB per meter, and that just corresponds to this 4.343 multiplied by 6 into 10 power 24, and it so happens that in this solution I missed out this overlap factor. So, you do have to multiply 0.9 to this multiplied by minus sigma As, right, and then from that you can actually figure out what is your sigma As. So, this number is slightly off, so this has to be multiplied or divided by 0.9 to get the final value. Do you understand what we did? Right. So, now that we know sigma As, now we need to find out sigma Es, okay, and for that we look at the case where N2 equals to 100%, because when N2 equals to 100%, if we go back and look at this factor is 1. So, sigma A and sigma A, these two factors will cancel, and then what will be left out is sigma Es, right. So, what is the corresponding gain value? I just go up in this and say the corresponding gain value is about here for N2. So, this 100% excitation corresponds to N2 equal to 1, this is N2 equal to 0, right. So, that is roughly about a factor of 4.5. So, once again I equate, I put it down as 4, but that should be 4.5. I equate that to this expression and from that we can find out sigma ES. So, 0% excitation corresponds to no pump power. So, without any pump power, right, the erbium silica fiber acts like a absorber. All the ions are in the are the ground state. So, any 1550 nanometer photon that comes by will get absorbed, and that is what you saw in your experiments the other day when you were actually doing this experiment on the EDFA. When there was no pump power, you actually saw that the EDFA, the so called amplifier, is actually providing loss, right. So, you needed to pump it to a certain level before you can recover back to the original signal level that you were sending in, and then you have to pump beyond that to achieve amplification. Okay. So, the other part is about assuming an average excitation along the length of the fiber as 60%, right. What is the length of erbium doped fiber required for achieving a gain of 30 dB? Okay. So, for that you go back and look at this graph. So, 60% excitation corresponds to, this is 0, this is 10%, 20, 30, 40, 50, 60. So, this is 60% over here, this curve corresponds to 60%. So, at 60%, the corresponding gain per meter that you have is 1.5 dB per meter. Sorry, which point? So, this is basically 0, 10, 20, 30, 40, 50, 60, right. So, 60 corresponds to this curve over here, and the corresponding point at 1550 is over here, that corresponds to 1.5 dB per meter, that is the gain you have. So, the question is, for that gain, so gain is 1. What is the length required to achieve 30 dB gain? You basically say 30 dB divided by 1.5 dB per meter, and so you need a length of 20 meters. So, this is typically the, as if you are designing an erbium doped fiber amplifier, okay, this is what you have to deal with. You are given this this graph, right, gain versus gain per unit length versus wavelength, and then based on that you are supposed to figure out what is the excitation level required, what is the length required to achieve a particular gain and all that. Okay. And this is of course for the simple case of uniform excitation, but if you are doing this for real, you know there is going to be a certain pump profile depending upon the pumping configuration, and based on that you will figure out what is the N2 and N1 at different points along the length of the fiber, and based on that you will figure out the overall gain. Now, a couple of points before we jump to the next topic. One is that if you look at the gain for an erbium doped fiber amplifier, what this tells you is that you can achieve gain over this region 1520 to about 1560 nanometer, okay, which is called the C band, okay, from an optical communication perspective. C band corresponds to the conventional band, okay. So, you can achieve amplification, and one of the things you see is that the gain is not uniform across that spectrum. So, if you have communication, if you are doing communication, you have multiple wavelength channels which is carrying information, they are all coming into this amplifier, and you would want to have constant gain or uniform gain across for all the wavelengths. So, what you normally have to do is to put in some loss element, spectrally dependent loss element, which actually provides loss such that these points the gain is actually reduced. Okay. So, if that gain is reduced only for these wavelengths, then you would have a relatively flatter gain for all the wavelengths. So, that is a process called gain equalization, okay, that is typically carried out in this in this amplifier. But the other interesting part is that when you consider this band from about 1570 to about 1620, you have very low gain, but you do have gain, right, and that actually is what you call as an L band amplifier. It is called the long wavelength band. Okay. But when you look at the long wavelength band, it's typically flat. The gain spectrum is typically flat. So, that means you can achieve uniform amplification over a wider range of wavelengths. Okay. So, and quite interestingly, if you think about it, if you think about what is this long wavelength band means, the long wavelength will correspond to really short transitions, okay, basically low energy transitions, right. So, this was basically something around 1600 nanometer. Okay. So, when we consider a pumping scheme like this or an amplifier like this, it is typically ending up as a transition, the transition is ending up over here, and then you have non-radiative relaxation that is taking you to the ground state. Okay. So, at the longer wavelengths, it's acting as if it's a 4-level system. Okay. So, it may be looked upon as a quasi 4-level amplifier at the longer wavelengths. And one of the properties of a 4-level system is that even for very low excitation levels you have gain, and that is what you see. Even for very low excitation levels you have gain. The gain is not very high because the probability of those transitions is very low, that the emission cross section is very low. Okay. But nevertheless, because it almost acts like a 4-level system, you can achieve gain at relatively low levels of excitation. So, a graph like this can teach you a lot of things. If you pay a little more attention and look at this you can learn a lot about amplifiers from a graph like this. And so, we have spent a lot of time looking at this graph. So, hopefully that's taught you something. So, what we are saying is the shorter energy transitions are likely to end up at the higher energy levels of this ground state manifold. Okay. And from that you would actually have a non-radiative relaxation to the actual valence level. Okay. So, from that is similar to what you have in a 4-level system. So, we have not defined 4 distinct levels, but it actually looks like it acts like 4-level systems because you are accessing only the top energy levels of your ground state. Okay. And I want to actually end this with one more point. So, you see that around this wavelength 1480 nanometer, so where was this? Is it here or maybe I am trying to look for this, here. So, around 1480 nanometers you have a significant absorption cross section. Okay. So, you can essentially pump at those wavelengths also. You do not necessarily need to pump at 980 nanometers. You can choose to pump at 1480 nanometers also, because it has got a very high absorption cross section. And what does that correspond to? So, instead of going all the way over here in the case of 980, what you are doing is you are doing this for 1480 nanometers. And what you see is that is okay, because the emission cross section is relatively low. So, it is not a 2-level system. Why? Because any photon, any atom that is pumped at 1480 nanometers will correspond to a transition from one of the lower energy levels of your ground state to one of the higher energy levels of the energy level E2, okay, from which you will have non-radiative relaxation before you try to achieve this gain, right. So, that is still a 3-level system, okay, and so you're not likely to achieve a lot of gain at 1480 itself, right, because that will correspond to a 2-level system. But if you are looking for gain at longer wavelengths, gain at these wavelengths in the conventional band or the L band, 1480 nanometer pumping would also be useful. Okay. It is not as useful or as efficient as 980 nanometer pumping, because at 980 nanometer the emission cross section is 0, virtually 0. Okay. So, it only contributes to absorption, there is no emission, whereas at 1480 there is a finite emission cross section. So, part of the light can actually come back as 1480 itself. Okay. So, it steals some of your inversion through that process, and because of that you do not achieve as much gain for the same level of pumping compared to 980 nanometers. Do you see that point? Okay. So, coming back over here at 1480 at that wavelength itself the gain is very low, but you can use 1480 as the pump to achieve gain at the C band or the L band. Okay. So, you may see commercial amplifiers with 1480 nanometer pumps also. Okay. I see that I have run out of time. So, we are not getting into this part, but that is okay. We can actually take care of that in the next lecture.